Hello all, and thank you for coming to this presentation. I'm Alex Harrison, a first-year PhD student with the Combustion Group at the Department of Chemical Engineering and Biotechnology, and today I'll be talking about our research in sustainable energy and chemical production. We all know the concentration of carbon dioxide in the atmosphere is too high, and in 2018, the global average concentration was 407.4 parts per million. However, due to increasing energy demands, more CO2 continues to be released to the atmosphere, and despite the increasing use of renewables and in their efficiency, global energy-related emissions continue to grow and in 2018 reached a historic high of 33.1 gigatons. This means that our renewables, such as wind, solar, hydro, and nuclear, which are carbon neutral, may not be good enough. We need carbon negative technologies, which have a net production of energy and net negative CO2 emissions. One way to achieve negative emissions is to use the energy from renewable energy sources in carbon capture units. For example, this one shown here, where we take the energy from the renewables, use it to absorb the CO2 directly from the air, which of course can then be stored or utilized. However, this process is highly energy intensive for reasons I'll discuss in a moment. But when we say the word combustion, the normal association is bad for the environment. But as a Part 1 student, you'll know this is not entirely true, as with the appropriate technologies, combustion processes can be fairly environmentally friendly. For example, in the combustion of biomass, the plant absorbs CO2 from the atmosphere, and then we release the CO2 when we combust it. Therefore, the combustion of biomass is carbon neutral, and indeed is renewable. And in fact, the combustion of biomass has a promising potential to achieve negative emissions. For when we combine renewables with carbon capture, we capture the CO2 directly from the atmosphere, where the concentration is around 400 parts per million, or 0.4%. This is very high in terms of climate change, but actually rather low in terms of the separation, which makes it very energy intensive to separate the CO2. However, if we directly capture the carbon from the exhaust stream of a biomass combustion, where the concentration of CO2 is around 10% by volume, this is greatly more efficient in terms of the separation, and as such is far preferable. In fact, if pure CO2 were released, we wouldn't need to separate it at all. We could store or utilize it directly. To achieve this, we use a process called chemical looping. In chemical looping combustion, we have one reactor called the fuel reactor, where we introduce our fuel, in this case biomass, and a solid oxygen carrier, for example copper oxide. There's then a combustion reaction between the fuel and the oxide to produce carbon dioxide and a reduced oxide. This reduced copper oxide is then passed to an air reactor, where it reacts with air to reoxidize the oxide and form oxygen-depleted air, and so close the chemical loop. But what we notice here is that we have inherent CO2 capture because we don't need to separate the CO2 in the exhaust stream from the nitrogen in the air, and as such, this chemical looping combustion is greatly more efficient. In our group, we focused a lot on investigating the fuel reactor and ways to make it more efficient. For example, we've conducted modelling and experimental investigations of the biomass particles and the ways in which they emit gas, i.e. volatilize, when combusting in the fuel reactor. We've also conducted detailed modelling on the reactions between the fuel particle with the chemical looping agents, requiring complicated mathematical simulation, and we're in the process of developing novel designs of fuel reactor to further improve the efficiency. But as well as combustion, chemical production has a significant carbon footprint, which we're looking to reduce with chemical looping. For example, we have several ongoing projects relating to epoxide production, where epoxides are important precursors in the later production of polymers. In a conventional epoxidation process, for example for ethylene, oxygen is directly mixed with the hydrocarbon over a catalyst bed to form the ethylene oxide. But this direct mixing of oxygen and ethylene is extremely hazardous and carries a large risk of explosion, and as well as this, we have unwanted complete combustion to carbon dioxide and water, which reduces the efficiency. In a chemical looping epoxidation process, the oxygen is directly delivered from a solid oxide, which greatly improves safety and allows us to have greater throughput, intensifying the process and potentially reducing the carbon footprint. We're in the process of looking into what other reactions can be improved by use of a chemical looping approach. Thank you very much for listening, and I do hope you'll join us next year If you have any questions about our research or about the chemical engineering tripos in general, please feel free to contact us with the details given on screen. Thank you very much for listening.